Okay.
Okay. May the 16th webinar on quantitative experimental design being presented by Dr. Brian Soblora or Soblora. If I say I don't never remember how to say it. Associate University Research Chair, Center for Interdisciplinary Studies, College of Doctoral Studies, University of Phoenix. With that said, we got 14 people attending this session. We are recording, and it's all yours.
Okay. Well, hello, everybody. Welcome to the session on quantitative experimental design. So I don't have to say anything more about the slide because Armando pretty much did all that already. So I will just jump right into the content. So, welcome to the quantitative experimental design webinar. This is just a continuation of the webinar series on the research methodology to help you in your research. So the focus of this session is to review the methods that's used in this design, and as well as some software to show how these methods are going to be used. So, like most of these methods here can be done in SPSS, the SAS Studio, a little bit of Excel, and other software packages. So I don't advocate a use of any software package. I think it's up to the researcher to make that determination, what they feel most comfortable with. So what's going to be the general outline of the presentation? Well, the first part is going to be the introduction and review of the quantitative experimental design. And then it's going to mainly consist of the one-way ANOVA and two-way ANOVA, multivariate analysis of variance, or known as MANOVA.
Hold on.
And then some brief.
Hold on, Brian. We lost the PowerPoint. Let me go in Plan B.
Again?
You keep losing it. Let me see if I can share it myself. 1 second. 1 second, please.
Okay.
Almost there. Give me 1 second.
Oh, okay. Oh, I got back in, Armando.
It's back. It's back. Okay.
So, as I mentioned, this is the general outline of the presentation, and it's going to be one-way ANOVA, two-way ANOVA, as well as the MANOVA, and some other methods that you can be used for randomized design. So I'm going to do a little bit of a review of the quantitative experimental design first. When do we use this design? Well, the premise of quantitative research is to determine the relationship that you have between your independent variables and your dependent variables in some population. But quantitative research design could either be descriptive, as we all know, or which just means you measure it one time, or you can have it as being experimental. So in other words, you subject to before and after case. So you'll be interested in knowing what happens before as well as after. And remember, a descriptive study just looks at only associations between the variables that you have in your research. But experimental design kind of goes a little bit further and it basically is trying to establish some causality between the variables that you have. So what are the variables that you defined and what's the causality that's going to occur between those variables? Research design is going to be the true experimentation because you're looking at the establishment of the causality or looking at the relationship between cause and effect among the variables. So in a purely experimental design, you always want to identify and impose control over all the variables except one. That's going to be the one that you're interested in. But the independent variable is what's manipulated you're doing. You're
We
sitting
lost it
there
again,
trying to.
Brian. Brian, we lost the PowerPoint again.
I know, I saw that.
Yeah, did you maybe inadvertently hit the stop sharing button?
Nope, I haven't done anything.
Okay, try to put it back in, please.
How, here we are.
Could it be the connection? Oh, there you go. It's back.
So as I stated before I got bumped out, is that we want to manipulate the independent variable to determine the effects on the dependent variable. But when you're looking at the quantitative experimental design, you have to look at efficacy versus effectiveness. So remember, efficacy is the benefit of looking at some intervention to control or a standard program under control, some sort of controlled randomized condition. So in that case, if you have that, you're probably be more interested in using more randomized controlled trial would be used. Now, effectiveness, on the other hand, if you're going to be the intervention is under less controlled real world condition. So that's going to be more of a quasi experimental design. And I'll be doing that on June 6, 2019. So the main emphasis is going to be on the first part, on the efficacy, looking at the effects of some control in an experiment and see what the outcomes are going to be from that. So here we have experimental design. So what do we mean by the true experimental design? Well, basically how it all works is we have a bunch of subjects and we randomly assign them to at least two groups, comparison groups rather. And the purpose is to compare two or more groups that are formed by some random assignment. So the groups are only going to differ based on some type of measurement. What's the intervention? So, for example, you give some sort of test, and you give a pre-test and then a post-test. So, do you want to know the result or the measure of causality between the pre-test to the post-test because of the intervention? So maybe it could be a new mathematical instructional tool. So you did a pre-test to see how did the students do without the mathematical tool for the intervention versus the one afterwards. You want to know what happened, what was the impact of that mathematical pedagogical tool. But a completely randomized design is just a simple version of randomized experiments. So what's going to happen is you're going to be more interested in the mean responses that actually occur in the design. So here's a simple illustration of quantitative experimental design. We're looking at some exposure to a new teaching method. Well, so you using this new teaching method, so the researchers will attempt to control the two groups, keep them identical as normal as possible, then allow one group to be exposed to the new teaching method. So by doing the latter, this enables researchers to isolate the effect of the teaching method. So you inject that teaching method, and then you want to know what the impacts are going to be or the outcome, which would be your dependent variable, and then the method and the group that are being manipulated by the teaching method would be the independent variable. But the control group should almost be identical to the experimental group. So the experimental group is exposed to the change by the researchers. So in other words, given this new teaching method, how did the students perform under that? While the control group just remains constant. They were not exposed to the teaching method. So the first type of quantitative experimental design that we're going to look at will be the one-way ANOVA. So what is the one-way ANOVA? Well, ANOVA is short for analysis of variance. So it's used with three or more groups to test for the means of differences. So for example, you might be looking at a caffeine study with three groups: no caffeine, mild dose, and then a jolt group. And the level is the value or the amount of the independent variable that you expose the groups to. Then the treatment group is going to be the people who get the specific treatment or the level of the independent variable. So you're having these three caffeine groups, and then you're going to expose them by the amount of caffeine and what are the effects of that. And then the treatment effect is going to be the size. It's going to be the size of the differences in the mean.
Now, you
And
lost the presentation, Brian. Again, can you please put it back in?
so here I am. So
Not there yet.
now it's saying that it's being
We got
shared.
it now. We got it.
Oh, you got it? Okay. So dv means it's going to mean the dependent variable. So what's going to be the rationale for the one-way ANOVA? We have at least three means test. So the null hypothesis is mu1 equals mu2 equals mu3. It represents each of the caffeine groups that I talked about. So the null hypothesis is going to say they're all the same. And then for the alternative hypothesis, all you have to say is at least one of the means differ. But we don't know which other means do differ. We just know there could be a difference. So we can take them two at a time, but we really want to test all three at once. So in other words, we can just simply do a t-test between two groups at a time. If we take them two at a time, then we're going to have a problem with the type 1 error going way up. So if we did it as a ANOVA or two-way ANOVA or whatever it may be, we won't have to worry about the increase in the type 1 error. So instead of using the mean difference, we can use the variance of the group mean about the grand mean over all groups. So the mathematics underlying ANOVA can be kind of tedious, so I don't show that. I'll just explain everything. And the logic is going to be the same as it is for the t-test. We compare the observed variance among the mean, observe differences in the means in the t-test, and then what do we get by chance? But remember, as I stated earlier, the alternative hypothesis says at least one of the means differ. The test will tell us, yes, there are differences in the mean, but it does not tell us where those differences are. And there's something called the post hoc test will come into play, and that will tell us where these differences are going to be. So continuing on with the rationale for the ANOVA, so we draw three samples from the same population, and we put them into three groups. So our results might look like this. So you can see there's mean 1, mean 2, and mean 3. So you have three distributions for the group, and the one that's going to be telling us the shape of the distribution is going to be the size of the standard deviation. That we can see that. So we can note that all the means from the three groups are not exactly the same. So from this picture, we have three different means, but they're kind of close, but the variances among them would be very small. So when you're actually using the ANOVA, it says the analysis of variance, but we're testing the mean. So what you're really essentially doing is you're testing the differences in the mean via the variances. That's basically what's going on with the ANOVA. So suppose we still have same people from three different populations. We might have results that look like this. You're going to have a mean 1, mean 2, mean 3 from three different distributions, and the variances are going to be different. But you notice here the sample means are all over the place here. So the variances will then be large. So because the variances are large, that will have an impact on your test.
We lost it
Uh,
again, Brian.
I know the little button went off on me. So when you're doing the testing, what's going to happen is you're
Not there
really
yet.
doing it from,
Not there yet.
so uh, how about now?
Brian is.
So when you're doing,
Yeah.
yep.
Yeah, it is.
So so then you're doing everything through terms of the variances. So suppose we complete some study and we find the following results. So we have two graphs here. How would you know if there's a real effect or not? Well, you can just simply observe the variances that you see, and what would you expect to get based on chance, given no two differences in the mean? So you just can't look at a picture and say, yes, there are differences, or no, there are no differences. That's a very anecdotal way of presenting it. What you kind of get guidance by the diagram to see what's going on in the plots, and then you can go forward with the hypothesis testing to see what the conclusion would be. And then, the mathematics underlying the ANOVA can be quite tedious. So, and all software packages will show the ANOVA table instead. It's providing SPSS, Excel, R, SAS Studio, or any other statistical package. So each type of ANOVA has its own table. This is just a general specification for the one-way ANOVA, and it kind of shows you the between groups, within groups, the mean squares, and then the f-test is just a ratio of the mean square and so on. So it's another way of summarizing the data. It's kind of nice to show. But as I stated earlier, if you reject the null hypothesis, then say there are differences among the mean, then you have to go through the post hoc test. That just shows you the multiple comparison. Well, the F-test is significant from the ANOVA. The researcher has a difference in population mean, but you don't know where these differences are. So the alternative hypothesis says, yes, you have at least one of your means are different, but you don't know which one. That's where the post hoc test comes in. So in SPSS, they have a feature to do the post hoc test. Unfortunately, in Excel, it does not have the post hoc test. But if you decide to do it, you can create your own worksheet to do that. But the more comparisons that you have to do, the more complex your worksheet shall become. SAS and R will also have features to do the post hoc test as well. And then, so when you're doing the post hoc test, then I would tell you where do these differences actually occur. And
We
then
lost
once you know that,
Brian. We
yeah, no,
lost.
I'm
There
getting,
he is.
I got.
He's back. Got to be careful with the little button,
So,
right?
mhm. So let's say you have three means. It could be A equals B is greater than C, or A is greater than B and C, or A is greater than B and B is equal to C. Well, we can test that. We need a test to tell where these means are going to be different. There are multiple tests to do this. So SPSS has like several different tests to choose from. I always use the common one because everyone knows how it works. So the post hoc procedure is versus the a priori comparison. We only look at the post hoc. And then we always want a comparison of the error rate. That would be the level of alpha for each of the comparisons. So the experiment-wise error rate can be expressed by the type 1 error, which can show you all the possible outcomes. So alpha error equals 1 minus alpha to the C, or to the comparison. But the nice thing is the SPSS does this for you. So how does it actually work? So we have A, B, and C, and the researcher has to do three comparisons, A to B, A to C, and B to C. It sounds pretty straightforward, but if you have to do this in Excel, it could be kind of tedious because you have to make sure you pick out the right numbers from the Excel output. But SPSS does it automatically. So without any adjustments, the error
Go on,
rate would be
go on,
0.4.
Brian. There you go. Thank you.
So that's how it works. So the most common method is going to be the Tukey, the HSD. So that's done in SPSS, and typically it's used for equal sample size per cell. And what does HSD mean? Honestly, significant difference. There's the formula here. Alpha is your type 1 error rate, which may typically be 0.05. And then Q alpha is the value from the table. SPSS and stats and all that will calculate that for you. And then MSW is the mean square error within groups, or the second row of the ANOVA table. And then N is going to be the sample size in each group. NA rather, sub A. So SPSS and other packages will provide you a post hoc test. All you have to do is select the option. But in SAS, you need to specify what the combination shall be. And as I said, Excel does not do these tasks, so you need to calculate it manually. It could be painful to do manually because the more comparisons that you have to do, the more tedious it's going to become. So we can conceptualize this. So this is from an actual course assignment in advanced statistical methods class I taught. And so does the independent variable belonging to a group, such as religion, social class, or race, explain the variations or the differences in the dependent variable of IQ. So the research question. So you remember your research question must align with your problem statement and your research purpose and so on. So for ANOVA, the research question is very, very specific. Does the average IQ differ among the working, middle, and lower class individual? Because you're looking at the average IQ among the three groups. And you have to be very clear in the research question to identify what groups that you're actually going to be testing. Don't just sit and say there's differences between the groups. You have to specify what is the variable of difference that you want to see. So hypothesizing the average IQ for each one social class is different from one or more social classes. And as I stated earlier in that slide, you need to make sure that your research questions align with what you're going to do in the ANOVA. So here's an example of a one-way ANOVA, a full-blown empirical example. We want to know, and this comes from a good book that I in statistics, and I got knocked out again. So I will go back in. So, so the one-way ANOVA, we wish to know whether drinking Coke, Pepsi, or OJ, or orange juice, increases the weight of rats. So you randomly assign 10 rats to each of the three treatment groups and give them Coke, Pepsi, or OJ for so many weeks. Upon the treatment they received and to know which of the means actually differ, if they do differ. So the factor is going to be the drink type, Coke, Pepsi, or OJ. That's the fit effect because we're not manipulating the Coke, Pepsi, or orange juice. I want to know the effects of these on the three types of different beverages. So using the SAS Studio, one-way ANOVA can be estimated. So I'll show you on the next two slides on how it was done. So here is the data. So the data is the name of the data set. You say data, and you can call it whatever you want. So the input is the inputting in the variable for the one-way ANOVA. So the input is the drink type. When you have a $sign after the drink, that the variable is nominal because it's the name. So SAS knows that it's a name. And then after that is the weight. So the weight based on Pepsi, Coke, or orange juice. And at the end of it, you put the semicolon and you go proc sort by drink. So SAS knows that you have three groups and they're sorted by that way. Then you can write a little SAS code. You go proc, so it means procedure, ANOVA. You're telling it to do the ANOVA. Class drink, because we want to do it by type of drink. And then we say model weight equals drink, tell it to do the ANOVA. Means of drink and HOV test Tukey. So the means drink / HOV test Tukey means that you plan to do the test for each treatment and apply the post hoc test Tukey in this case. So proc ANOVA initiates the one-way ANOVA in SAS. Class is the treatment variable. Model is the modeling the effects of drink on weight of rats. And the means is telling you calculate all the averages of each drink, the effects, and apply the post hoc test, Tukey. And you can change the post hoc test to whatever you want. You just go in the SAS manual and find out which one you wish to pursue. I always do Tukey. So here is the output from the SAS procedure. And it tells me the number of observations that went in. And then typically when we're doing this, the only thing we're going to really be interested in is the PR is greater than F in the ANOVA table. So in other words, the significance, the p-value. So let's formulate the null and alternative hypothesis. So the null hypothesis is that mu of Coke equals mu of OJ is equal to mu of Pepsi. What are we saying? They're all the same. The weights are all going to be the same. Then the alternative hypothesis, all you have to do is say at least one of the means differ. We don't know which ones, but we know one of them may differ. So the results from the hypothesis test shows the p-value is less than 0.05, 0.001 in this case. It's very small. So that tells us we reject the null and conclude that at least one of the means shall differ.
Lost it
But
again.
we don't know which so we don't know which ones differ. So that's where we go to the post hoc test, and then that's what I'm going to show you once I get my screen back. So the ANOVA procedure will show you the student HSD test for the weight. So it controls for the type 1 experiment-wise error. So it generally has a higher type 2 weight than the regular weight. So here's some diagnostics. And then on the bottom it says Tukey grouping, the mean, N, and then the drink. So from the Tukey task, all of the means are different from each other. How do we know that? Because if you're looking at means are all going to be the same. So if under the mean column, if it said AA and then a number, that's telling you there's probably going to be no differences and there's nothing that happened. But in this case, all the mean does not have any letterings in it, no A's or B's or C's. So if the means is showing the number, because of the numbers, that tells you there's going to be differences among all of the drink combinations, the pairwise combination. So that's going to be the one-way ANOVA. So the two-way ANOVA. So the two-way ANOVA, the effects of two factors can be investigated simultaneously. So the two-way ANOVA or can belong to some gender or whatever it may be. So you're looking at these two factors together. So you belong to a group and it's going to be by gender. So so kind of in statistical theory, when you're doing something like this, really what you're doing is you're trying to remove some of the variation that actually occurs. So to look at both factors together is the two-way ANOVA, which is compared to one-way ANOVA, only one factor. The two-way, you're looking at two factors. So when you have two, what you'd be interested in is knowing how it's going to impact.
We lost it, Brian.
I know, I'm going back in.
Can someone please
So,
mute their phone? It's a noise in the background. Please mute your phone, everybody except Brian, please.
so continue on with the two-way ANOVA. So we have the effect on the population mean of so looking at the dependent variable. And we can look at how all this is going to be attributed to the factor alone. It's going to be called some like perhaps two one-way ANOVAs. So as I stated earlier, in statistical theory, when you integrate two factors like this, what's going to happen is you're trying to reduce the amount of variation, if possible. So what are the hypotheses for two-way ANOVA? Well, two questions are answered by a two-way ANOVA. Is there any effect of factor A on the outcome, the main effect of A? And then you do the same, is there any effect of factor B on the outcome? So the main effect of B. So that means so when you're doing a two-way ANOVA, you know you're going to have at least two sets of hypotheses. And then another way, which I didn't show here, is that you can also look at the interaction between A and B. And that'll be your third hypothesis for a two-way ANOVA. So, so that makes kind of things more exciting. So in a two-way ANOVA, you're going to have at least two F tests. But if you're testing for the interaction between A and B, then you're going to have three F tests. So, so you're going to deal with two sets of hypotheses now. So here I took the hypotheses, the mean effect of A. So the null is saying alpha 1 equals alpha 2 equals alpha 3 equals 0. So we're saying that everything's the same. Then the alternative hypothesis is going to say not so. There's going to be at least one that's not going to be significant, or it will be significant. So the main effect of these is we're going to do the same thing. The null hypothesis is saying, hey, everything's the same, nothing to worry about. And then the alternative is going to say, hey, something is different here. And then if you have the interaction effect, then you'll have a separate hypothesis for that interaction effect too. So more specifically, the hypotheses now are substantiated in the previous slide. So I was showing you what the hypotheses would then look like. So we can conceptualize the two-way ANOVA. So there's two independent variables, political party and gender, with a dependent variable attitude about the tax cut. So the research question that aligns with the two-way ANOVA. So again, you have to make sure your research question is going to align with your problem statement, purpose statement, and so on. You just don't make up anything and try to figure out that you have to do a two-way ANOVA. So the kind of research question that you may have for a two-way ANOVA, is there an interaction between gender and political about the recent tax cut, which is going to be your dependent variable. But you're hypothesizing that gender is one variable that looks at tax cut and the other is political party. Gender is one way, but then you can also look at it in terms of a political party. And then someone can make an argument and say, oh, you know what? Educational status is going to matter too. That could be another independent variable. So could you have three variables to look at and doing an ANOVA? Yes, you can. You can have a larger ANOVA to assess. So you can make the ANOVA complicated as much as you want, depending upon what variables that you have that actually make sense, that coincide with the intended research. So what's going to happen now, I have to get back in again. Give me 1 second. So you can make the ANOVA as complicated as you want, but you got to keep in mind it must be able to align with your intended research. That's what you want to make sure. So the more that you conceptualize it and narrows with or agrees with your problem statement, purpose statement, and so on, the better.
Not back, Brian. Not yet.
I'm back.
No.
So example of a two-way ANOVA. So I'm going to take the rat example that I used earlier and expand it. So let's expand the rat drinking experiment. So that this time the rats are given two treatments. Factor one, we'll give them Coke, Pepsi, or orange juice, and then we're going to say, hey, let's give them exercise. Let's make that factor two. So you either have exercise or no exercise. So in this experiment, 4 different rats are assigned randomly to one of the 6 treatment combinations, and then you just weigh them. And then I have the data on the next slide. All the data for orange juice to come out. For some reason, when I made a picture out of it, I think somehow something got screwy. You have Coke, Pepsi, and orange juice. Then you have columns for no exercise and exercise. Then within each group for Coke, exercise, and Coke and no exercise, we weigh the 4 rats. And then we're going to wind up with several groups that we see here. Well, given the data using stats again, And then you have data rats 2, the input drink, exercise, and exercise is going to be nominal variables. That's why we have the dollar sign again. So yes or no. And then you have the weight. So then you can write the stats code, proc ANOVA, class drink, exercise, because we have two variables that we're looking at, drink and exercise. Model weight equals drink exercise, and then drink times exercise. So you model the statement because you're looking at the interaction between drink and exercise. You do it for drink, exercise, and then the interaction between drink and exercise. Then you have means drink slash Tukey. You want to take the drink, the averages of the drinks, and then we're going to do the post hoc test using the Tukey. So you still use the proc ANOVA. This is the same. The specification is a two-way model because we have two treatment terms. We have drink and exercise. So in the class statement, there's two variables. Stats will know, hey, we're going to have a two-way ANOVA. And then we want to look at the interaction effect of the drink and exercise on rats. And then we tell it to do a Tukey test. So do you have to do an interaction test? No, you can still just do it as drink and exercise. But I wanted to show you that some people get excited because they want to know if there's perhaps any type of interaction that's going to occur between drink and the exercise of rats.
Put it back in, please. Yeah, you go.
So so that's what we're telling it to do. We're telling it to do. It's going to be a two-way ANOVA. And then here's the output. The output for this is horrendous. So I only show a little piece of it. But the interpretation is still the same. So looking at the p-value, the two-way ANOVA indicates that both the main effects and the interaction term are statistically significant. They're very small, or well less than 0.05, I should say. Because the interactions are statistically significant, you should still do the post hoc test, yeah, of course. But look at the interaction term first, then you look at the other variable. That's typically how you would do it for a two-way ANOVA. Look at if there's some interaction going on, what's going on here. And then you can look at the drink and exercise by itself. And then here is the Tukey test. And what's happening here under the column where it says Tukey grouping, we're noticing that there's a repetition of the letter of the group. So therefore, this indicating that the means of the same letter are not going to be that statistically significant. So we're going to see, so there's not going to be a whole lot of interaction going on, or I'm sorry, not interaction, but post hoc comparisons that can be found between the variables for the rats. So that takes care of everything on one way or a two-way ANOVA. So why did I spend time on that? That tends to be common to research design that's used in doctoral dissertation research. And then I've seen some of it for faculty when they do their research projects. So another common approach is the multiple analysis of variance. It's an extension of the ANOVA in which the main effects and interactions are assessed on a linear combination of the dependent variable. So in other words, we have more than one dependent variable in ANOVA. ANOVA, you only have one. And then now that you have more than one dependent variable, you can create combinations of them and assess it that way. So the MANOVA tests the mean differences among groups basically on the combination of the dependent variable that we see everything else in statistics that occurs by chance. So what's going to happen is now you're typically going to have more than one dependent variable, more than you would have compared to a ANOVA. So back into going into ANOVA. So more on the MANOVA rather, it's a little more technical side of it. So when you create a new dependent variable, that's going to be a combination of the individual dependent variable because you want to be able to maximize those differences between the groups that you have. Also, when the independent variables have more than one level, you can actually take all your dependent variables, combine them to maximize pair comparison. So in other manipulations of the dependent variable for the use of your grand mean to show if there's any differences that actually occur. So one of the things that you have to keep in mind is that the dependent variable must be continuous. And what's going to happen is that the differences on the theta variable are assessed for two or more discrete groups. In other words, an independent variable. As a side note, there was a faculty member that actually applied a MANOVA to non-continuous data. Is it possible to do that? And the answer is probably yes. You can probably do something like that. There's no non-parametric test equivalent of MANOVA. So in theory, you can use a MANOVA for that type of data, non-parametric data. But you have to be careful of your assumption that you use because you're not having normality distributions and so on and so forth. So you need to be careful on that, on those interpretations. But I'll save that for another day. So what's the advantages of MANOVA over ANOVA? Well, you want to measure the dependent variables. The researcher increases the chances of finding some differences in the group. But with a single dependent variable, the researcher does not put all your eggs in one basket type approach. They're saying, okay, you have different combinations of the dependent variable. Where are the differences that actually are going to occur? So the multiple measures usually do not cost much more than it is otherwise. So you can probably actually do find a difference at some point.
Put it back in, Brian, please.
Huh?
You lost
Oh.
it again.
So I'm still here. I can see it. So using multiple ANOVAs rather than just a single ANOVA, you're going to get a larger type 1 error. So if you just use a MANOVA, you reduce that. So under some conditions, some people say if you show MANOVA has differences, that they may not show up under ANOVA. So that's kind of rare. So that something like that will occur. So when you're doing a MANOVA, you have to be careful of one thing. You got to know which dependent variables are going to be important. Hey, if there's a significant main effects or interaction, what is going to be caused by the different independent variables? But so you can follow a significant MANOVA with an individual ANOVA to see which of the dependent variables has and see what the effects are going to be. You can actually do that too. So, so, so you have to be. So when you're doing a MANOVA, what you're going to keep in mind is what you're trying to do is going to be looking for the differences among the dependent variables that you have and see what's going on here. And then once you have that, then you can figure out what's going on. So you can conceptualize the MANOVA. This is from an actual dissertation that I was involved with some years ago. And the gist of the study was to investigate the mean group differences in the scores for the OSRI. It's a survey instrument for EA professionals. And the independent variables were age and gender. And then there was 3 dependent variables: occupational stress, psychological strain, and coping resources. So, what was the research question? So, what would kind of a research question that you would have for Manova? Do the group mean differences between the three EA professionals, age group, and burnout? So, let me get back in.
Are you there, Brian?
Yep, I'm here. I'm getting back into the PowerPoint.
Brian?
Yep, I'm here. You hear me? Hello? So, anyway, so they're back to the research question. So, to do the stress, the psychological strain, and then the coping resources. So this is from an actual textbook from Morrison's Multivariate Statistics. It's actually a pretty good book. And I have lots of nice examples in there. So I took it right from there. A researcher assigns 24 subjects to one of two groups for the effect of a drug type. The first group receives a drug for the effect on females, while the second group receives the drug for males. So the researcher looks at the effect of this drug by gender to determine if there's any differences of the effect of the drug type. So that's what they're interested in. So here's the data. Sorry, it's not that great. I mean, it was hard to make a picture out of it. And then you can see you have the sex or gender, the drug type A, B, C, and then the males and the females, the impacts on the variables on them. So So now, so you can have data Morrison, which is the name of the textbook, input sex, then you have the dollar sign because your sex is going to be the male or female, drug, the drug type ABC, so dollar sign, and then you create the input variables that you might have. And then you have the data, proc print, and then proc GLM, data equals Morrison. So proc GLM is going to be generalized linear models. So in man, so in stats, it's going to be a general linear model that's going to be used. You have classes, sex and drugs. Then you model it depending variable. That's how you would know there's going to be two dependent variables. You use them both at the same time. Then you go sex, drug, the two classes, and then you have the interaction between the two, which is sex times drug, and then you do the mean, and then you could run MANOVA and you specify the MANOVA statement. So each row in the data here, so you have M M M F F F F. It's for a single person, and it shows the effects of each drug on the by gender. The stats code looks the same for ANOVA, but the proc statement's a bit different. The class statement shows two treatments, gender and drug type. And then the MANOVA is going to be the GLM procedure. And then the model statement tells you this is what we're going to estimate using MANOVA. And here is the output. So anytime you do MANOVA test, no matter what software package, it's Wilks Lambda, Pillai's trait, Hotel and Lawley trait, and Roy's greatest root, and it shows you the impact. And some people only like the Wilks Lambda test because it's calculated exactly, and the other F values are not or approximation. And there's a lot of statistical theory behind that because the Wilks lambda is the exact statistic. It's based on an exact distribution where the remaining three are not. So also the ANOVA is, if MANOVA is significant, the researcher can probably use an ANOVA to see what's actually going on. But you can see here all the p-values for all the tests shows it's not significant. So the researcher cannot use an ANOVA. It's pointless. So other approaches, so this is the materials by Rubin. So all the material on this part here, Rubin's work and so on, are looking at causal inference known as the Rubin causal model that's coined by Holland in 1986. It's using quantitative type statistical and econometric analysis. So here you're looking at more on the causality and you're using a totally different estimator. So some of the one common estimator that would be used would be the difference in difference estimators. So that is a whole new ball of wax, but you still, the goal of the difference in difference estimator is to say, okay, we impose this before and we impose this after. What are the effects? We can look at the differences in differences from that. So the importance of Rubin's approach, it shows the assignment and the treatment and the potential outcome. So as we saw with the other methods, MANOVA and ANOVA, it's still going to be randomized. So RCN uses potential outcomes because one of them could be observed and basically assigned to a group. So Holland calls the fundamental problem of causal inference. Basically, he says what? For individuals we observe under treatment, we have to form an estimate of what they look like if they didn't receive the treatment. That's the fundamental problem of causal inference. So there's a good paper by Imbig and Woodridge in 2009 that looks at the social outcomes of all these types of looking at causal inference that you could see in these type of design. So what role does it play? It forces you to think about the causal effects. In some cases, we're going to be more interested in the causality. What causes what and why? That's what we're going to be interested in. And the second role is basically looking at the treatment effects. Well, you don't always know all the uncertainty that's going to happen in your data. So sometimes you see something that goes on, but you're not sure. So you have to model that uncertainty, and then you want to know how it's going to affect the differences in differences estimator that's going to be used. There's other estimators besides DID that you can use too. Then there's recent advances in this area, and there's quite a bit. You can use instrumental variable methods, panel regression, regression continuity designs, quantile, and so on. So a good book for that would be Angrist and Pischke. They cover these methods pretty well that fits the quantitative experimental design. There's some caveats on what we did today. Well, I didn't check the assumptions for the ANOVA and MANOVA. So you need to do that when you do your research. I glossed over that. So if you don't test the assumption, you may get misleading inference in your test result. Then you might want to check the plot to see what's going on as well. I kind of skimped on that too. So, but when you're doing the actual work for your thesis or whatever it might be, you need to check it. Sometimes there's repeating measures. This is tricky to do because you got to be careful. So you can do it in ANOVA and MANOVA, no problem. But the problem is, a main thrust is that you have to make sure that you have the appropriate sample size. And then once you have that, you'll be fine when you're doing the repeating measures. And then that's everything I have to say for today. For now.
Hey, Brian, this is Ryan Rominger. Armando's having some trouble, so I'm going to step in here. Thank you for your presentation this evening. And I was wondering if are you open to taking questions?
Yes, I am.
All right. Are there any questions out there for those who are still here? Like, about Carr.
Yes, hi, how are you?
Good.
I am wondering how this will apply to a pilot test. And that's the first part of the question. The second part is how many people will it take to make a pilot test effective?
So what was the first question again? I'm sorry.
The first question is, will all of this work with pilot testing?
with a pilot
Uh,
test?
it,
Pilot
so,
test is a,
what will be the scope of what you're trying to do? Maybe that might help me to answer the question.
sure, sure. I have pre-test, post-test dealing with blood transfusion and how surgeons respond to Jehovah's Witnesses who don't accept blood transfusions in emergencies. So the idea is to give a pre-test to establish baseline, and then an educational intervention on the whys and wherefores, the pros and cons of blood tests, rather blood transfusion, and then the post-test after that. Two groups, as you mentioned, control as well as the experimental group. Now, the witnesses make their natural experiment because they naturally don't accept blood transfusion. So they would be, as I stated, the control group. Now, before I do a full-blown experiment, it's my understanding that roughly it's about 30, subjects you have. I'm guessing for each group or 15, split them in half. But I was told that I should probably, since my instrument is new, the educational intervention, since that's new, that I should pilot test it first.
Oh yeah, you
And
should if it's brand new. But you that before you
yes,
actually
sir.
collect your data and before doing the pre-test and post-test using ANOVA or MANOVA or whatever method that you wish to do.
Yes, sir. That's exactly. Um, what I'm wondering now, I guess I surmise that everything you mentioned actually apply to the pilot test. But my question, I suppose, that I'm asking now is, what is the, I guess, number? How many people should I have for a pilot test in order to test out my instrument?
Oh well, I think that's gonna. I mean, usually when you do a pilot test, you don't really sure that whatever you're doing in your survey instrument is telling, getting the data that you wish to have. So there's no hard, clear-cut answer on how large your sample should be, but I have dealt with some the dissertation on that, and I typically say just to be safe. I mean, if you
Hmm.
can get 30 or perhaps a little more than that, that might be sufficient. And then when you do the pilot, if it's okay, then you can probably confer that it's going to be okay to do. But if you notice there's some problems that might be emerging, well, then you may want to think about doing another field test before you do anything.
Okay, so just so I can be clear here, and I'll get offline after this, or let someone else ask a question. Uh, the It's my understanding that you have 30 for the field test for the full-blown test, but before you have 30, at least in my case, I've been asked to have to pilot test it. And I've read where a
Right.
pilot test, you might have as few as, I don't know, 5, 10 people. But I'm not sure about that. So that's my question to you. And incidentally, I've already finished my dissertation, and I have been well, I have grant money uh, earmarked for my research, but I have to go, of course, through the IRB, and that's the process. That's where I am now. But in the application it says, hey, you have a new instrument, so we want you to pilot test it first. So I suppose, once again, to be very specific, I'm thinking, or I read, where a pilot test, the number of people that I can use for a pilot test could be as few as 10, we'll say. Does that sound reasonable to you, sir?
Uh, I had students that did pilot tests too, for new survey instruments, and I was kind of always saying I'd rather that way.
Okay,
I mean,
great.
I don't know. I think a sample size of 10 might be kind of small. So, and
Okay.
I'm not. I suspect it may have some impact on your reliability and validity.
Yes, sir. Okay. Okay, great. Thank you very much. I appreciate it.
Oh, no problem.
Are there any other questions?
If
Brian, one of the
not,
things. Oh, is there a question?
is this, yes, is there some way we can contact Brian, or if that's okay if we have questions, follow-up questions?
Oh, you can. I have my email address on the final slide. You can contact me. It's Brian. It's B as in boy, S as in Sam, LOBODA at email.phoenix.edu. You can contact me then.
Great. Okay. Thank you. Thank you very much. I appreciate it. I had a pen that did
No,
not work. If you don't mind, could you say that one more time? I'm so sorry.
B as in boy,
Yes.
S as in Sam,
Okay.
L
Hmm.
O B as in boy, O D as in David, A at email.phoenix.edu.
Got it. Thank you very much.
Brian, one of the things that I've heard discussed, Dr. William Broad, who is a research methodologist, used to say this, and this actually has to do with Furpo's question about a pilot study, is that if you make no changes, if you find out that your pilot procedures are working and everything is copacetic, that you can actually integrate that pilot data into your main study. Do you have any thoughts on that?
Uh, I always like to do the pilot tests and the actual data collection. I'd like to see them to be separate. I I don't feel comfortable about taking the, even though it's 100% perfect and so on and so forth. I would rather to just take that new instrument and go out and get a whole new sample of data and don't and try not to rely on the field test data. That's my kind of thing. I mean, my student tried to do that one time. I said, no, you need to go out and get all new data.
It's an issue with the IRB too. I'm sorry. I apologize. Something happened with my computer. I had to log back on using my phone. IRB will not allow you to use the pilot data into your
Right,
study. Uh, they allow you. As a matter of fact, you need IRB permission to do the pilot, but none of the
right.
subjects that participated on the pilot can belong to the experiment later.
Mhm. Yeah, I always, that's what I told my, I didn't say this to my student about IRB. I just said, please go out and use this instrument and get all new data. And he did that.
Yeah, I find that curious from a research perspective because I don't see procedurally, I don't see any reason why that data would necessarily have to be excluded from a statistical reason if the procedures are identical.
But,
I understand
but,
the
uh,
IRB
but,
piece.
but, again, I mean, could you actually use those, uh, respondents from the pilot test and include them into your new sample and they do it again? I don't have a problem with that. But to actually take the data from there and move it over, some people may have an issue with that. Like Mondo pointed out, IRB might have an issue with that.
Yeah, no,
And then I always tell my students, to just go out and get all new data. Don't cause any problems. It makes it more.
yeah, no,
I
and
feel better, and then he feels
you
better.
don't want you don't want to tussle with IRB.
I tell you something. That's easier said than done with regard to getting some totally different subjects. The reason I say that is because, as I stated, my dissertation was actually it was qualitative, so I interviewed several surgeons, but it was like pulling teeth because no surgeon wants to be viewed as, hey, I want to see how you work under stress when you get a client or get a patient, pardon me, who's one of those witnesses who won't allow you to give them blood transfusion in a life or death situation. How are you going to handle that? I had to, jump through a lot of hoops just to interview a few surgeons. So getting 30 of them together might be, one heck of a, feat to pull off. But, I'll see what happens. But that's what I'm hearing you say, that you need 30. It ought to be interesting to see how it turns out.
Well, you might be a non-parametric too, like running Kruskal-Wallis or I forget what the other one is. Right, Brian?
I know what it is. I can't think of it. I can't think of it off the top of my head either. I always have I'm bad with names on the non-parametric test, but I know which one you're talking about.
Man Whitney and the Kruskal-Wallis, I think, are the two that come to my mind.
Yeah, Man Whitney.
Oh, that's interesting. And good. Maybe I can get another email address from you as well, sir. The moderator. I'm sorry.
Oh yeah, my name's Ryan Rominger, and Brian's gonna know the statistics much better than I. Just so you know, I do more with qualitative and mixed methods, but you're welcome to email me. It's Ryan, R-Y-A-N, Rominger, R-O-M-I-N-G-E-R 440 at email.phoenix.edu, and I can put that in chat.
Okay, great. Thank you. I did write it down, but that'll be correct. Wonderful. I don't recall what those two methods are, or those two approaches that you mentioned. I do remember reading about them some time ago, but anything that would make my job a little easier would be great, and I am looking forward to getting this past the IRB. I actually have to take the city test again because it expired, but I have to move forward on this to get it done. This is great motivation. Thank you so much for letting us know about this whole presentation here.
Yeah, thank you. I realize that we're almost a quarter past, so Brian, thank you again for all the information, and the slides and the video will be up on the Research Methods site. So go ahead and look for that information there. And thank you, everybody, and have a good night.
All right, good night.
Okay, bye, everyone.